Okay, welcome to the second video that reviews the potential energy difference in chemical reactions, and in this particular video we're going to review the endothermic reaction condition. Alright, the potential energy difference. So what we're going to do is just quickly review this, and the reaction of interest is going to be the one where we take ammonium nitrate, which is an ionic compound that has an ionic bond, and we're going to dissolve it in water to form these ions. We're going to have a change in compositional potential energy because we're going from an ionic bond to bonds between ions and water. So there's a change in the bonding between the ionic compound, where we have an ionic bond, to a new bond which is between the ions and water molecules. Okay, to set this up, we're going to have a glass of water. Okay, and that represents the surroundings. Into this glass, we're going to place the ammonium nitrate. And I'm going to just diagram it here as a big old box. This is our system. The system is always the reaction. And in order to have space, I'll put the reaction down here. Okay, now, if you were holding this glass of water in your hand, and I'm just gonna say that we're starting out with this at room temperature, so it's around 25 degrees centigrade. In your hand at that point, the glass of water is not going to feel much different in terms of temperature than your hands. Not much different. Yeah, I mean, you're not going to pick up the glass of water and go, oh, this is cold, or something like that, or oh, this is hot. And then what we're going to do is add the ammonium nitrate to the water and allow it to dissolve. As that happens, you're going to feel the water in the glass cool down. It's going to become cold. So the temperature of the surroundings goes down. It goes down. The glass is going to feel cold. Now, what's going on with that? The reason why the temperature of the liquid is going to go down is because, let me change the color of this, is because there's going to be a decrease in kinetic energy. And where is it going? It's going into the system, and it is coming in here in the form of thermal potential energy. It's going to lift the products to a higher potential energy than where we start with the ammonium nitrate. If we were to graph this, and we put potential energy on the vertical axis, and we pick a point anywhere on here to show, where we're starting. So this is the ammonium nitrate. This point here is 0. And I'll just define this as being PE1. Where this is going to finish, our products are going to be on a line which is above the reactants. All right, I'll put a big fatty R here to mean reactant. So up here it's going to be NH4 plus NO3 minus. Let me just fix this so it looks like a 4. Okay, now if I draw a line over, this is PE2, and you can see clearly that there has to be an increase in potential energy to go from PE1 to PE2. This is above PE1, which is above 0. Now, if I take this line out here, you can see, all right, if we were to subtract these two values, this difference right here is the change. This is your kinetic energy. that moved from the surroundings into the system, right? This came from, let me just put absolute words on this. This comes from the surroundings. So for an endothermic reaction, the products are at a higher potential energy than the reactants. Exclamation point, exclamation point. In fact, let's put a third one in here. All right, and with that concludes the quick review.